Okay, so my son's favorite superhero is Batman. Why isn't it playing? Play.
Yeah.
So he's still in training. But that pertains to today's lesson, so I thought I'd show you a little Batman. My son loves Batman. Okay. So we're talking about multivariable functions. What is a multivariable function? What do we mean by a multivariable function? When you say multivariable, what is that referring to? Do you remember? She said more than one input. Agree with that? Yeah, more than one input. And so specifically right now we're talking about real valued multivariable functions, meaning there's more than one input and then the output or the dependent variable is a real value. Okay? And so we talked about, last time we talked that there's four representations of these. We got the definition as a formula, the function definition. This is just an example, right? So we could have any combination of x's, y's, constants, any types of functions could create a multivariable function. This was just the example of our basic paraboloid. We could have a graph in R3, right? How do multivariable functions graph in R3 as what kind of thing? Surface, right? As a surface. And then we talked about level curves, right? So if you take traces for constant z values or constant values of the output of the function, you get curves, xy curves, right? Curves like in the xy plane. If you put them all together, that makes what's called a contour map. Contour map is, so we'll see lots of those. And we got to a table of values, right? So then a table of values is another representation of a multivariable function. These are the main four. So then, now we're going to get to the calculus of multivariable functions. We'll start with rate of change, right? Rate of change of multivariable functions. So let's just review rate of change in general. The meaning of rate of change. So you're traveling on a highway and an app on your phone tells you you're currently moving at 90 feet per second. What is 90 feet per second? That's the rate of change of distance traveled in feet with respect to time elapsed in seconds. Okay, but what does that number 90 mean then? So 90, yes, 90 is the rate of change of number of feet with respect to number of seconds gone by. What does that number 90 mean? Yeah?
For every change in seconds, you're moving 90 times feet for that.
Okay? So talking about a change in seconds. Good, okay? So does it mean that every additional second that goes by means an additional 90 feet traveled? Does it mean that? Okay, but is that the broadest meaning? Is that all we know about 90 feet per second? Yeah. All right, it's a constant rate of change. That's true, constant rate of change. This is a narrow meaning, okay? This is a really narrow meaning of that. But unfortunately, it's the meaning that most people have. They say, oh, every second means you go 90 feet. Every second that goes by means you go 90 feet. But this is a very narrow meaning. And so Alex was getting at a better meaning, okay? He was talking about, so do you know how far you go in 2 seconds at this constant rate? How far do you go? So you know more than that you go 90 feet in 1 second. Do you know how far you go in half a second? 45 feet. Do you know how far you go in a third of a second? 30. How about a tenth of a second? So you know a lot more than just every second that goes by, you go 90 feet. What? You know how far you go in any change of time, okay? So that's what we mean by dx. Any change in time that goes by, you know how far you would go. How far would you go in any change of time? Or how much would your change in distance be in any change of time? So how did you figure all those out? 90 times your change in time, right? So you know that the change in distance is 90 times whatever change in time you chose, or you were looking at. So this is a broad meaning, right? This is a broad meaning. It tells you everything you could know about 90 feet per second, meaning you know how much your change in distance is for any change in time, not just 1 second. So here's a good meaning for a constant rate of change. For any small change in seconds, the number of feet is 90 times the change in time. And so I say small change because, you know, in a second or two, your app could be telling you a different rate of change, right? And then it wouldn't work for 2 seconds or 3 seconds or whatever. But if for a moment there it's 90 feet per second, then you could pick a small change in time in that vicinity, in that moment, and you could say this is true. So as we're working on all this stuff with rate of change in these multivariable functions, we have to have this baseline understanding down. So two variable, real valued functions have this form we talked about last time. Z is a function of x and y. This is how we conventionally write them. 2 input variables, and then we use z to be the corresponding value of the output. So what are we going to do? We're going to look at rate of change of what with respect to what? If we're talking about rate of change of a multivariable real valued function at the form z is f of x, y. We look at the rate of change of what with respect to what? He wants the rate of change of z, first of all. Agree with that? Yeah, rate of change of z with respect to? Okay, so x, we're going to start with x or y, okay? And eventually we'll get to x and y. But we're going to start with or. We're going to pick one. We're going to look at the rate of change of z with respect to x. And we're going to look at the rate of change of z with respect to y. That's how we'll start off. Keep it simple, okay? But then we'll start combining them, okay? So the rate of change with respect to x, then we know what? For any change in x, we're looking at the corresponding change in z, and we'll know that by the rate of change with respect to x, so I'll call that m sub x, okay? M sub x. And then likewise, if we make a small change in y, if we knew the rate of change with respect to y, then we could get the corresponding change in z. So it's always the change in output for a change in some change in the input. So for a function like this, then we actually have 2 derivatives, or 2 rates of change. One rate of change for changes in x that give the change in z, and one rate of change for y would give the change in z for a change in y. So we call these partial derivatives. So we have the partial derivative with respect to x. That's that mx, I'm calling it. And then the partial derivative with respect to y, my. So partial derivative, because it doesn't tell the whole story about how changes in z can come about, right? It's only, we're just looking at the part of it where we say change x and see what happens to z. And then the other part of it is where if you change y, see what happens to z. So then what does that, if I change x and I'm looking at changes in z, what does that mean for y? What does that mean for y if I'm changing x and analyzing the change in z for a change in x, then what about y in that case? Yeah. Yeah, we're going to keep y constant, right? So we keep y, don't change y, that will just complicate the matter, right? So keep y constant when you're analyzing changes in z for changes in x, and likewise keep x constant when you're analyzing changes in z that come from changes in y. So making a small change to x to apply mx requires keeping y constant, and vice versa. Okay, so we have notations for partial derivatives. So this is lowercase delta, Greek lowercase delta. So this is partial of z with respect to x, or if the function name was f, we could say partial of f with respect to x. Or maybe the most common, the easiest, is uf subscript x. That refers to the partial derivative with respect to x. And then same with y as the same one. So learning about how to partial derivatives, we're going to be looking at partial derivatives through the lens of the 4 different representations of multivariable functions. Right? So function formula, what do we say? Graph in R3, contour map, graphs in R2 with the constant z values, and then table of values. So all those 4 representations, we can investigate and look at partial derivatives in the lens of those different representations. So recall the 4 primary representations. We've talked about them here. And so we're going to determine and analyze partial derivatives in each of these contexts. We'll go back to that one later. I'm going to start with this one. So here's a function definition here's a nice application of multivariable function. The displacement in millimeters of a point on a guitar string, x millimeters from the end of the string, that's our first variable, y milliseconds after the string is plucked, that's our second independent variable. It's given by this function, right? So the dependent variable is height of the string from the at-rest center line. Let's draw this out here. So you got the string like this. And so here's one end, say, the other end. And so x is going to be how far we are from the end of the string. Y, again, is going to be some time since the string was plucked. And then combining those two things, combining a distance and a time, gives you some displacement from center line, or where the string would be at rest. So at some time after plucking it, say the string looks like that. We freeze time. So then the values of g are, so given an x and a time, values of g are the displacement of the string. So this is g, x, y. So that right there, that vertical displacement, is a dependent variable. Okay, so here's that function as a formula. So we want to find the partial derivatives. So we'll start with, say, gx. Okay, we could also call that, we can also do that this way. So both those mean the same thing. So we're going to think about what does it mean to look at how z changes with respect to x. What does that mean for y? So as we work on this derivative, partial derivative, then how will we consider y? Constant, right? So this sine of 2.765y is that's going to be constant. So this whole thing is constant, just like the 3 is constant. So this 3 and this sine now, for doing the partial with respect to x, we're going to treat the whole thing as a constant. And when a constant is multiplied by a function, you're taking the derivative, what do you do with that constant? Let's multiply. take it out. 5x cubed, derivative of 5x cubed. Do we take out the 5?
Oh.
Just stays around, right? You just hold on to it, right? It just stays there, right? So the 3, so we're going to have 3 sine of 2.765 y. Then what? Now we're ready to do derivative. Derivative of sine is cosine. Are we done? Chain rule, right? Times derivative of the interior, right? Derivative of the interior, pi over 100. So you're going to follow your same rules from Calc 1. But you have this added dimension here that the extra variable that you're not considering, you have to treat it as a constant. So you do everything the same that you would do with constants before in those rules. But it stays as that letter, right? Okay, so partial with respect to y. You do it, take a minute to do it, and then we'll see how you did. So you do the partial of g with respect to y. Okay, Travis, did you get this one?
No.
You get started? You do it on the fly here?
Yeah, sure. So it would be 3 negative cosine.
So are you working on this, or are you working on this? We're doing the partial with respect to y. So what happens?
Oh, yeah, I was starting with y.
So what happens with that?
Would it stay the same?
It stays the same. It's just a constant, right? And then we get to this, and that's a function of y, so derivative of sine. Try again.
Cosine.
Just cosine of
2.765 y times 2.765.
there you go. Agreed? We good? Okay. So now we want to evaluate those. We're going to do some analysis here. So you got those written down in your notes. So I can erase this. So I want you to find and interpret. We're going to split up here so we can just g of 70, comma 2.5, the partial of x at 70, comma 2.5, and the partial of y at 70.25. We're going to find those values, and then we're going to interpret those. And this is not a simple thing, right? There's a lot going on here. And then in the interpretation of these numbers in the context, it's a mouthful. In order to get it specifically right, there's a lot to say, okay? So we're going to practice. So in terms of getting the values, let's split up. So you guys over there on your left, on the left side of the room, you guys find the function value at 2.5. Make sure your calculator is set to radians. Everything here is going to be radians, not degrees. Middle of the class, if you're somewhere in the middle, you guys do the partial with respect to x at 72.5. And then over here on the right, the partial with respect to y at 70.25. And once we get those numbers, we'll share the numbers with each other. And then we'll work on interpreting these numbers. So confirm among yourselves, or among the people around you doing the same thing. Again, make sure your calculator's on radians. Radians, not degrees. See that? Okay, Winston, what do you think? 1.635. 1.635. Someone else get that? Someone on the left, same thing? You got it? 1.42. That's what Jackson, is it? 1.42, is that our consensus? I'm going with that. Someone else get 1.42? Let's get one more person. 1.43. And then what are the units on that? Millimeters. Okay, in the middle, the partial with respect to x at 770 and 2.5. Anyone got that number? In the middle. Yeah, tell me.
Negative 0.033.
-0.033. Someone else? Andrew got that? Thumbs up. Ryan? All right, negative 0.033. What are the units on that? The partial with respect to x is the derivative. What will the units be on that? What's that? Meters per second. So what is this? This is like z with respect to x, right? The rate of change is the change in z with respect to x. So should be changes in z are measured in millimeters. Changes in x is x seconds. Changes in x are millimeters. Do we want to cancel them out? No. Z is millimeters, like displacement of the string. X is millimeters down the string. Totally different, right? So millimeters up and down per millimeter this way along the string. Last one, with respect to y. Partial with respect to y. Anyone got it over here? Got the number? Shout it out. Yeah, tell me. Ashish. 5.425. Anybody else get that? Alex got that too. 5.43 units on that. Millimeters per millisecond. And that's positive, right? Okay, so now I'm going to take attendance, and I want you to do the hard work of interpreting these numbers. It's not easy. There are a lot of details here. Okay? Each of these numbers relates back to the 70 and the 2.5. Okay? And we want broad meanings, right? Not narrow meanings, right? We want broad meanings for each of these numbers. So take turns. Even if someone you think does it really well, don't be done. Now you try, right? So then come back and you try to say it. Okay? Go. Everyone gets a partner. Talk these out. What do these numbers mean? Milliseconds. Right. 2.5 milliseconds after plucking the string, and 70 millimeters from the end of the string, that point is going to be displaced 1.43 millimeters. Well, that was the easy one. Whew. Okay. So how about the partial with respect to x? Christian, did you get this one?
Yep.
Tell me.
So
what does this number mean?
This number means how much the string displacement in the z direction for any change in the like towards or away from the end, how much the displacement will change.
Okay.
So by negative 0.033 times the change.
Okay. A lot of good stuff in there. Somebody else? Jose, same one. What does negative 0.033 millimeters per millimeter mean?
It means that if you increase, like if you go further down the string,
right,
you'll be moving closer to where the string is at rest.
Okay.
And if you move backwards along the string, you'll be moving farther away.
Okay. And if you move further down the string, how much will the displacement change?
At that instant, it's changing 5.033 millimeters per millimeter you move on the string.
Okay. Yeah. Jonas.
So at
at the point where you're 70 millimeters away from the end of the string,
Right.
and 2.5 milliseconds has passed,
Right.
and there's a small change in the, or where you pluck the string at,
Right.
where the displacement on the point where the string is at is going to be negative 0.0 or 0.033 times that number.
The displacement will be? It's not like you said the displacement will be negative
Oh, it
0.0.
changes.
The change, right? The change in displacement. Yeah, so at 2.5 milliseconds, 70 millimeters down the string. If you made a small change in distance down the string, the change in displacement that you would see would be negative 0.033 times as much as the change in distance down the string that you picked. Did you catch all that? The key to it is dy equals m dx. Or in this case, dz equals mx dx. That frames the meaning of that number. And then there's the other details of that we're 2.5 milliseconds after 70 millimeters down the string. We're going to make a change in distance down the string. The change in displacement of the string will be that rate of change times the change in distance down the string that we picked. Okay, so let's try the next one. Gy. Yeah, Alex.
At 70 millimeters down the string,
Right?
at 2.5 seconds, for any small change around 2.5 seconds, the change in displacement will be 5.43 times that change
In
in time.
time. Good. You got it. Someone else want to try? Jorge's like, no. Eddie, you want to try it?
Okay. So it's like the displacement of z for time y at 2.5 milliseconds, 70 meters down by 70 millimeters down.
That's true. That's true. We want to frame it this way. Given any change in what? Time from 2.5 milliseconds, given a small change in time from 2.5 milliseconds, the change in displacement of the string will be like 5.5 times as much as the change in time that you picked. That's what that rate means. Okay, I think we're moving closer to the goal there. So let's go on here. Any questions on that? Does that make sense? We'll keep practicing that. That's important. So let's go to Batman. So here's this function, ln of 1/3 x times x minus y squared to the 1/3. So again, let's practice finding the partial with respect to x, the partial with respect to y. And so now I have natural log, so this is a function of x, if I'm doing partial with respect to x. I've got this first function is a function of x, this second function is a function of x. Therefore, to get the derivative or the partial with respect to x, I'll need product rule, right? Product rule. So should we do derivative of the first will be 1 over 1/3 x times 1/3 times the second. And what happens to the y here? Constant. So if there was a constant there, what would you do with it? It would just stay in there. So imagine this is x minus 4 or x minus 100. It would just stay, right? In this particular context, right? So derivative of the first times the second plus the first times derivative of the second. So what's the derivative of this? 1/3 x minus y squared to the negative 2/3 times 2y times the derivative of the interior with respect to x. Just 1, there's nothing, right? It's just the derivative of x. It'd just be 1. If you wanted to write 1, you could, or just nothing. Okay, you guys do the partial with respect to y. So the partial with respect to y. Product rule? You need product rule? No, because this is not a function of y. It's just consider it a constant. All right, questions on this one? Yeah, please. Did I make a mistake?
Natural log 1/3 y and not natural
X. It should be x. Do I have it right now? Yeah, so derivative of the first times the second plus the first times the derivative of the second. All right, so now let's do the partial with respect to y. Here you don't need product rule because this doesn't have any y's in it. So it just is a constant multiplied by our function of y. Chrissy, did you get it? Tell me.
1/3 times.
So what happens to this in the partial with respect to y?
As it is.
Yeah.
So natural log of 1/3 x
Right?
times 1/3 parentheses x minus y squared to the negative 2/3, and then times negative 2y.
So when you started, was it this 1/3 you were saying? Okay, sorry, I didn't realize that. I thought you were doing something else. Agree? Make sense? Okay. So in WebWork, you'll have more practice of these, maybe a few harder ones, but you're going to follow all the same rules you did before. The other variable, you have to just treat it as a constant. That's the name of the game. Okay. Any questions on this? Okay, so back to here. Okay, so here's super easy now. These should be easy. So find the partial with respect to x for h, function h, and partial with respect to y. What do we think? Agree with that? So what about now we're adding a constant? So this is like plus 8 will be the derivative. What's that? Yeah, so when you add a constant, derivative of a constant function is 0. So that'll be gone. Are we good? All right? HY. Megan, did you get HY? Where did I lose you? So the 3x squared is fine, right? How about the minus 4xy squared? Is that okay? Because your 4y squared is like the coefficient of x, right? So this is like minus 4y squared x. So the derivative would just be the coefficient. And then when you add a constant like plus 100 or plus pi or plus whatever, that derivative would be 0. So, Serenity, how about HY? Did you get that?
Yeah, I got negative 8xy plus 4y.
Agree with what she did? Okay. Lots of nods. Thumbs up. Okay, so now we want to maybe. So let's find both of these at 1, 0.5. So at 1, 0.5, let's find the values. Some of you do hx, some of you do hy, so we can get the numbers as fast as we can. As soon as you get a number, shout it out. this positive 2, the first one?
Yeah.
Do it in my head. What's this? Minus 4. I don't know what that is. Negative 4 something, negative 3 something? What? Negative 3.5. Are we good? So I could have you practice this, but I'll just go for it. So what does this mean? It means when x is 1 and y is 0.5, if you change x a little bit, then what? The change in the function value will be 2 times however much you changed x. That's what that rate means. This means that if when x is 1 and y is 0.5, if you changed y a little bit from the 0.5, then z would change negative 3.5 times as much as the change in y. So the next thing we want to look at, I want to graph, so the next representation is the surface, right? The surface in R3. So let's look at this function in R3 and this point and see how we interpret or see rate of change on the surface. Questions on the arithmetic here? We good? So here's that function that we just found the partial derivatives for. Maybe. Oh. Right? X cubed minus 4xy squared plus y to the 4th. And here's that function. And then here's the point. What do we do? 1.5? There's that point. Does it show up? There we go. See it? Okay, so that's 1 and 0.5. So what can we say about, by looking at the surface at that point, what can we say about the partial with respect to x? What's true about y? We're doing the partial with respect to x. What do we say about y? Hold it constant at 0.5, right? So that would be like the plane, looking at the plane, y equals 0.5. See that? So this is, so when you do the partial with respect to x, at a particular point, then all you care about is what's happening at that particular y value. So do you see this trace? That's the intersection of those two, of the y equals 0.5 and our actual surface. And so how do we interpret the partial with respect to x by looking at that? What's that? Yep. But we're looking at the partial derivative of z with respect to x. So how does that, or what can you say about that? What's that? Going to go up or down, right? So here's the x-axis. For a change in x, what happens to z? For a positive change in x, what's happening to z? Did you see that it goes up? Yeah, and so what does that mean about the partial derivative? Positive, right? Positive. What did we get when we found it? What did we get? We got 2, right? And does it look like a rate of change of about 2? Let's see if this shows up. So here's our x, right? Does that show up? Beautiful. Okay. For a small change in x, does it look like z goes up twice as much? Yeah, right? So this is trace along the surface for this constant y value. For a little change in x, z goes up twice as much as the change in x. So that's how we see that value 2 on the surface. So what about analyzing the partial with respect to y? What should I do? X equals 1, right? So I'm going to look at the plane for x equals 1. And what am I going to do? I'm going to let y do what? Change a little bit. If I go in the y direction, so something like that, what happens to z if I do that? It goes down a lot, right? So here's, if I let y go up, increase a little bit, then my z is going to go like down that much. What was our partial derivative with respect to y? Negative 3.5. So for every little change in y that I pick, the change in z is negative 3.5 times as much, going down. So when you analyze these partial derivatives on a surface, you're imagining holding the other variable constant. And what's the trace that you would get on the surface? Along that trace, then, you can analyze the derivative just like you did in the Calc 1. Given that change in x or that change in y, what does z do on the surface? Keeping the other variable constant. So you can see things like positive rate of change, negative rate of change, zero rate of change. Okay, what about for our guitar string? Here's the guitar string function. And there's the point. What point were we looking at? 72.5. 70 millimeters down the string, 2.5 seconds. So what's the partial derivative with respect? There's the point right there. Does it show up? Yeah. What's the partial with respect to x? Looking at the surface, would it be positive, negative, or zero? Looking at the surface. So if you go a little bit in the x direction, you head down, right? So like a trace on the surface would be like this. Does that show up? Not really. You see that you're heading down there at that point? And what was our partial with respect to x when we did the negative 0.033, right? So it goes down a little bit when you increase x along the surface. And then for y? So in the y direction, do you see we have something like that? And does that show up? So if you let y change a little bit, then what about the surface? What does it do? Does it stay constant? Does it go down? Does it go up? And if it does, up a lot, up a little? It's heading up sharply, right? So for a positive change in y, you get a big change in z up, according to the surface there, holding x constant. And that's what we find. It was like 5.5, right? The rate of change was like 5.5.